Hello guys, welcome. My name is Shakti Sharma. Today we will study one very important topic and interesting topic of graph theory of finding shortest path from single source. And we will see this algorithm with one example. Okay, so algorithm name is Bellman-Ford, and the example here I have considered is one from my examination, which I took for the second year BTech students. So this is one of the graph and these are the edges given in this particular order to be relaxed. So what happens in Bellman-Ford algorithm that we relax these edges in the given sequence for v minus 1 number of times. So now here the number of nodes are 1, 2, 3, 4, 5. So 5 nodes means we will relax 4 number of times. Now after 4 number of times we will try to relax edges one more time, that is the 5th time. If there is no change, then we want to say that our result is good and that is the final say shortest distance. But what will happen if we find that the edges in the end of the 5th iteration they change, the weights, the distance to each node is changed, or any of the node is changed? That means there exists a negative cycle in the graph. So we can also determine the negative cycle by this method. So Bellman-Ford is particularly helpful when there are edges with negative weights and it's a complicated graph. So it can detect the negative cycles as well as it can find the shortest distance if there is no negative cycle. In case of negative cycle, there is no uh, true distance to nodes of the negative cycle because the number of iteration you took in the negative cycle will give you a negative and a smaller value. If you go for infinite times in the negative cycle, it will give you minus infinite value. So if there exists a negative cycle, then there is no true distance to any of the node of the negative cycle. So let's see this with one example, with this example here. Okay, so now initially if I want to put the distance, so first we need to initialize. So given that S is the source, so the distance to the source will be 0 and distance to all other nodes in the beginning is infinite till we don't know and we don't have access to all the node. So far we know that we are standing at the source node and we don't know the cost of reaching to all different nodes. One very good example you can consider in graph algorithms is that you can consider each node as one of the city and S is a source city. So you can say if you are sitting right now in Greater Noida, you can say that your source node is Greater Noida and the other nodes can be Delhi, can be Mathura, can be Agra, Meerut, Ghaziabad and so on. Okay, now you want to find the shortest path of reaching from one city to another city. Now some city where you can directly go, so if there is a say direct path from Greater Noida to Noida with a cost of 2, you can reach directly to Noida. If there is a path from Noida to Delhi, then you have to first go to Noida and then from Noida to Delhi. Okay, so it is simpler to understand this example with positive weights. Then you can say consider the time consumption is one of the say cost to you. Another example can be say the distance between city as one of the cost to you, which can be in a positive value. But how to consider these negative value? So we have to take little more complicated example here. The example comes from the military application. So if there are military tanks, those can or troops, those can travel from different locations. Now the consumption of resources from one location to another location is given in a positive uh, value. However, at some bunkers you get access to some of the resources. However, there will be definitely fixed number of resources, and it cannot go to minus infinite in that case. But some bunkers, they have some ration stored for you. So when you go to a particular bunker, you can get some resource, and then these values got added to your value. So those resources will be in negative. So what I mean here is that if you are moving from, say, bunker S to bunker B, then you are consuming 2 units of resources. So this is the cost. But from bunker B to D, there is some in between, there is something where you get 2 units of resources. Or you can consider if you spend 2 units of resources, you get 4 units of resources. So ultimately you are getting 2 units of resources. This is coming as negative. Okay. So after this examination, if we see how to solve this problem, so we need to relax these S's into given order. So now if I want to relax an SDE, what is the meaning of relaxing an SDE? So it is simple that we need to calculate the value of, so there is an edge D to E, so that means it will impact on the cost of the distance to node E. Now, how will this cost change? So we have to compare between two values here, which is the cost of edge E in the previous iteration, okay, or the existing cost of D to E, comma, we have to see what if we consider the edge DE. If we want to consider the edge DE in order to reach to node E, that means I have to first reach to node D with a cost D, distance to D, plus from there I have to take the weight of edge D, comma E, and this edge cost plus the cost of reaching D will give me the final cost of reaching to node E. Okay. Maximum, here we are trying to find the minimum cost, so I'm putting it as minimum. So minimum of reaching to node E directly or reaching to node D and then from D to E. So this is how what I mean when I relax the edge DE. So let's see. So the initial value of DE is infinite, so there is no change. So minimum of the first value is infinite, second value is coming as infinite plus minus 3. So this value is again the infinite. So there is no bigger value or smaller value if I add or reduce some constant value in infinite. So value will still remain infinite. So these both values are infinite. There is no change. So if I want to say relax the next stage, then so this I have changed the color of the pencil. So here this is infinite, so this will not change. Then the next value which we will relax next edge is BD. So on relaxing BD, infinite minus 2 in the same way will remain infinite, so there will be no change. So then third value which we relax is EB. Now EB, if we relax EB, infinite plus 4 will not change anything. Now the next edge we can relax here is SB. Now if we relax SB, 0 plus 2 will give me a value 2, which is definitely lesser than infinite. So there will be an update now here. And this value will change to 2. Now the next edge will be BC. So if we see BC, now if you see this particular example, so if I want to relax, say, edge BC and I want to find the cost of reaching to node C, it will again come from minimum of cost of reaching to node B, which has been updated now, and the updated value is 2 plus the cost of B to C, which is 6, comma the direct reaching to node C, which is right now is infinite. So we have to compare between these two numbers. So now 6 plus 8 is a small, so 8 will be the updated values. So this value here will change to 8. Now we relax, the next edge is SC. Now if I see SC, this is 0 plus 3 is 3, earlier value is 8, so 3 is a small, this value will change. Okay, so the new value is 3. So this is the first iteration we have completed by relaxing all the edges in the given format. Okay, so now I'm removing the previous weight, so it would be simpler to see for the next iterations. So these are the new weights. Now again we try to relax the edges in the same way. Okay, I'm changing the color of my pencil. So here also I can rub the, okay. So now again, so first we relax DE. Now relaxing DE will not give me much because the cost of reaching to node D is infinite. If in any relaxation, if reaching the source here, so there are two nodes in an edge, source and destiny. Source node cost is infinite, that relaxing that edge will not give me anything. Now the next edge is BD. When I relax BD, this will be 2 minus 2 and value will become 2 minus 2 is 0, which is smaller than infinite. So I will update. The next edge, if you see, is EB. When I relax EB, this is infinite plus 4, so will not change anything. Next edge is SB. If I see SB 0, 2, it is already 2, so there will be no change. BC 2 plus 6 is 8, no change. SC is 0 plus 3 is 3, already 3, so no change. So we are done with the second iteration. So here I can mark the first iteration. This was the second iteration. Now we will go for the third iteration. So there was only one change in the second iteration. Let's see the third iteration. So now relax DE. So 0 minus 3. Now the value will be minus 3, which is less than infinite. So this value will change. Okay. So when we relax DE, the relaxation will be BD. If I see relaxing BD, 2 minus 2 will be 0, so no change. The next relaxation will be EB. So minus 3 plus 4 will give me 1. Okay, earlier value was 2, so definitely this value will change to 1. And we can relax EB. Then relaxing SB. Now SB is 0 to 1, so which will not change. Relaxation of BC will again not change because 1 plus 6 is 7, the value is 3. Relaxation of SC will give me a value 3. Okay, so there were two changes in this particular iteration. So I can rub this and this. Okay, and we are done with iteration number 3. Okay, let's come back to iteration 4. So we need to relax the edges again in the same order one more time. Let's see. So relaxing edge DE. Okay. So 0 minus 3 is minus 3, no change. Relaxing edge BD will give me 1 minus 2, which is equals to minus 1. So this value will 0 to change to minus 1. Minus 1 is smaller than 0. It's a negative quantity, right? Then we go for EB. Relaxing EB will not change anything. Minus 3 plus 4 is 1. Then relaxing SB. SB is again 2. The earlier value is 1, so no change. BC, no change. SC, no change. And we are done with the fourth iteration. Now this answer should be the final answer because we have relaxed all the edges 4 number of times. But wait, we have to check for the negative cycle here. And for that, we have to go one more time. So let's see. So 0 relaxing DE here. Okay, so let me rub this. So relaxing an edge DE here. So when you relax DE, it is -1, -3, -4. And now since you are getting an update here, that means there exists a negative cycle in the graph. Okay. So if there is a negative cycle, that means that there cannot be any true shortest distance from source to all the nodes. Okay. And reason is that this negative cycle, if you want to see this as a negative cycle, B to D, D to E, E to F, E to B, the cost is -2, -3, -5 plus 4, that is -1. So the cost of this negative cycle is -1. So as many loops as I want, I will go in this negative cycle, and each time my weights of these nodes will change by -1. So will reduce by by value 1. Okay. So right now it is 1. If I go one more time, it will become 0. One more time, then it will become -1. Similarly, this value from 0 to -1 to -2, and it will also change in the same way. So all values will decrease by value -1. Okay. So this is what happened when we have identify a negative cycle in Bellman-Ford algorithm. Okay. So it detects and it tells, say, there is no true shortest distance from source to all the nodes because there exists a negative cycle, or simply it can say that there exists a negative cycle. So it will be there exists cycle. Sometimes it is easier to identify a negative cycle by just viewing at a graph. So here this was quite obvious. If somebody has paid significant attention in reading the graph or looking at it, then they could easily identify that there exists a negative cycle. But sometimes in a more complicated graph with more number of edges, more number of vertices, it might be very difficult to find the negative cycle in the graph. Now remember that negative cycle and negative weights are quite different. Uh, if I change this -3 with a value -2 or 1 or -1, then this negative cycle will be removed, and this graph will become a graph with negative weights, but no with negative cycle. Okay, so this particular example you can remember for identification of the negative cycle, and this is one of the major algorithm on other similar algorithms which are used to find the shortest distance. Now, the application I say are particularly restricted in the areas where there can be negative weights, because for most of the application, the weights, if it is described as cost, will be positive. Okay, so limited to the application standards, this is the major use of the Bellman-Ford algorithm. Okay. And sometimes it is also used to validate the, say, as a final step of some other algorithm just to find the shortest negative cycle, if there exists any negative cycle, because some of the algorithm, they ignore the idea of the negative cycle or the negative weights. So that is it for today's lecture. Post your comments if any, and or if you have better example. So it is always good to code these algorithms for larger size of graph and larger size of say set of edges. Here we have very limited number of edges. So if it is a very complicated graph, it is always good to write an algorithm past the variable values and then simply check what is the answer of the algorithm. Before any implementation, you must also understand the usefulness of any of the algorithm. Okay. Okay, guys, good luck.